Hello, this is the sixth lecture in the series of the course Tribology for the Beginner. In this lecture, we'll be discussing the influence of surface energy on adhesive and abrasive friction. Adhesive friction we have discussed quite a lot in the previous lectures. Here we'll mostly discuss about abrasive friction and the influence of surface energy on adhesive and abrasive friction both. Let me go to the next slide. Now, before we go to discuss the effect of surface energy, let's discuss a little bit about what is surface energy. Surface energy is basically the excess energy usually given in joule per meter square at the material surface, which is not so within the bulk of the material. Within the bulk of the material, a molecule is surrounded by other molecules, and hence they are completely bounded. Whereas a molecule on the surface is not bounded on all sides, and hence on the surface there is an excess energy available. And this is what the surface energy is. In a way, we can also discuss or define surface energy as the energy required per unit area to create a new surface. Because when you create a new surface, you are opening up so that the surface molecules are not completely bounded. Okay, having said that, let us go to the adhesive and abrasive friction. We have discussed adhesive friction, but still for the sake of completeness, we'll just have a quick look at adhesive friction. Adhesive friction, as we have discussed earlier, is in the macroscopy scale, is due to the solid state welding at the top of the asperities. If you look at this picture here, a blue surface is put on the red surface. Both are uneven, and the points of contact are very few. And at those points, the load is heavy, and hence the contact pressure is very high, and therefore the yielding may occur, and we may have welding due to plastic state of material. And we get usually a bond. So here in this picture, we get several bonds wherever the two surfaces are in contact. And the adhesive friction, in a very simple way, may be defined as the force required to break these bonds. In fact, when a body slides over another body, at the interface, there are many different phenomena taking place. For example, surface molecular forces, fatigue, plastic deformation, elastoplastic deformation, and many other phenomena takes place. But there are two main types of friction that we considered here on the adhesive and abrasive. So going to the adhesive friction, we can write that the coefficient of adhesive friction is F by W. In the picture, F, as we discussed, is the force required to break those bonds. Therefore, if AP is the area, or AR is the area, contact area, multiplied by the yield shear stress of the bond, and W, the normal load, will be again the AR, that is the contact area multiplied by PM. PM is the plastic yield stress, plastic yield stress. So therefore, AR cancels out, and we can write that the adhesive coefficient of adhesive friction is tau y by PM. Now, this we can see more clearly in the small picture here, where we have shown a hemispherical asperity being loaded by load W, and it creates a surface at the contact A. Or this area is the real contact area. I mean, the sum of the small areas of contact at the asperity tips are the total real area of contact. And this is given in this equation as AR. Okay, so this is fine. This expansion is fine as far as we are talking about the macroscopic aspect of the adhesive friction. But if we consider the microscopic or nanoscopic consideration, or even the atomic model, the surface molecular forces come into play, and we shall have to discuss this in different light altogether. This will do it in later lectures. Now, since we have already discussed adhesive friction, let us have a brief look at abrasive friction. Abrasive friction is often described as plowing friction, because what happens here is a hard asperity digs into a soft metal, and when it is slid or a tangential force F is applied, some metal is plowed out, just like what we have in plowing the field. This is why it is called plowing friction. So if we consider both of frictions, we can say that the total coefficient of friction, mu T, is equal to mu adhesive plus mu plowing or mu abrasive. Now, mu adhesive we have already shown to be tau y by PM. Tau y is the yield shear stress of the contacts divided by the hardness. PM is the hardness. Now here, one small thing must be mentioned, which we didn't discuss earlier, that when we talk about adhesive friction, we say that the force required to break the bonds. Now the bonds may not break at the junction itself. It often breaks at within the bulk of the softer material. And therefore, in most cases, tau y would be the yield shear stress of the softer material. Suppose we are plowing or we are rubbing rough steel surface on a smooth copper surface. Then it will be copper which will be plowed or subjected to abrasion. And therefore, their tau y will be the yield shear stress of copper. Now let's come back to mu plowing or mu abrasive. Now look at the picture on the right-hand side. Here we have shown a hard asperity digging into a small soft metal surface. Now here we show it as a conical surface, and the height of indentation is h, and the diameter to which it has indented is given as small d. Load is W and F is the frictional force. So mu ploughing is equal to frictional force divided by load. So frictional force is simply the projected area multiplied by hardness, because again what it is doing is it is ploughing, and hence there has to be plastic deformation, and therefore the projected area of this cone would be a triangle of height h and base d, small d. So the projected area is half hd multiplied by pm, pm being the hardness, and the load, vertical load or normal load, is pi d squared by 4 times pm. Pm is again the hardness of the plastic yielding. It is quite clear that when the hard asperity digs into the small and the soft surface, there has to be plastic yielding or plastic deformation. That's why the load is the projected area pi d squared by 4 times pm, the hardness. So then this gives mu ploughing as 2h by pi d. Therefore, the total coefficient of friction is tau y by pm, as we have said before for adhesive friction, plus 2h by pi d. Now this we can also denote in terms of the geometry. If we take the angle of inclination of the asperity being theta with respect to the horizontal, then the projected area would be, during ploughing, would be half d into d by 2 tan theta, because here h is d by 2 tan theta. So there, mu p or mu ploughing is d squared by 4 tan theta into pm. Pm is again hardness, and the vertical load, as before, is pi by 4 d squared pm. So this gives tan theta by pi. So there again, the total coefficient of friction is mu adhesive plus mu ploughing is equal to tau by pm plus tan theta by pi. So this is a very simple way of representing the two coefficient of friction, which is the basic of friction. So let's go to the next slide. Now here we consider the surface energy that we discussed earlier. Now when two smooth and clean surfaces are brought together, surface forces come into play. Long range or short range intermolecular forces come into play. Now this is not obvious in our everyday life. If we put a duster on the table and try to pick up the duster, we don't have to put an extra force other than the weight of the duster. But if the intermolecular forces were active, then we had to put some extra force in. This does not happen. This is because when the two surfaces are in contact, they have to be very smooth and very clean for the intermolecular forces to be operative. They have to be smooth because the roughness will not allow the molecular forces to be active, because molecular forces will be active within few angstrom. And the contaminant layer will of course do the same problem. They will not allow the two surfaces to come close enough for the intermolecular forces to be operative. However, if the two smooth and clean surfaces are brought together, as I was talking about the duster and the table, if they were clean enough and smooth enough, we have to apply a force slightly more than the weight of the duster. This is called pull-up force. We have to apply a slightly higher force to overcome the force of the intermolecular forces. We have to overcome the intermolecular forces. The intermolecular force against the distance between the molecules are shown in a graph here, which is a very well-known graph. And C here is the equilibrium position, equilibrium distance. Below C, there will be repulsion, and above C, there will be attraction. So we can see that the total force that would be required would be sum of the force up to the distance which we are applying. So this is a very typical and very well-known force distance diagram, molecular force distance diagram, and this we'll discuss in more details later. Surface forces or the surface molecular forces influence the surface configuration. And both in adhesive and abrasive friction, this will have a great significance. Because if the contact area is increased or decreased due to the forces, extramolecular forces, the frictional force or the coefficient of friction will be different. Again, we'll go into the detail later on. For the time being, let us look at the influence of surface energy on abrasive friction. Following Rabinovich, we consider a small indentation of a hard conical surface, conical asperity, on a soft metal, as shown in the figure. The asperity makes an angle of theta with the horizontal surface, and it indents up to a distance of x, and the diameter of the indentation is 2r. So this is the details of the contact between two surfaces A and B. We consider one single asperity. Now here, the work done is obviously W times X. W is the load and X is the deformation. And energy absorbed in deformation is pi r squared P dx. P is the contact pressure. So pi r squared P is the force. And we are integrating this up to whatever limit or whatever distance we have indented to. So it will be pi r squared P dx x1 to x2 or 0 to x1, whatever distance we have indented to. Now, surface energy, here we are given it as EAB, is usually given per unit area, will be dissipated because two surfaces would be lost when we are making contact. Now, surface energy per unit area, gamma, is given as gamma A plus gamma B minus gamma AB. Gamma A is the surface energy of surface A, gamma B is the surface energy of surface B, and gamma AB is the surface energy of the interface. Therefore, we can say that EAB times pi a square, pi r square. Pi r square is the contact area for the single asperity, as it can be seen in the figure, is equal to gamma A plus gamma B minus gamma AB into pi r square. Therefore, we can write that in general, area A times EAB is equal to the total energy or total surface energy. So if we differentiate U with respect to x, we get the separation force. As we said earlier, that when the surface molecular forces are active, we have to apply a pull-up force to separate the two, and that force will be given by du by dx. Okay, so this is the picture of the effect of surface energy on abrasive friction. Let us go a little bit more into the detail. If we consider the energy balance, the energy that is appearing as heat is Eg, is equal to Wx minus integral of pi r squared p dx, because that is the because as you have seen before, that is the energy absorbed in deformation. So that has to be subtracted. So Wx is the work done minus energy absorbed pi r squared p dx plus the energy, surface energy. Again, if you go back to the previous slide, you can see that the surface energy which is dissipated is given by EAB per unit area. So we can write EAB into pi r squared. So the total energy which is coming out as heat is equal to Wx minus integral of pi r squared p dx plus EAB pi r squared. Now, if we consider the minimum energy consideration, that is the usual way of optimizing, we take dEg by dx equal to 0. Now, in the first equation, integral of pi r squared p dx, r is a function of x, and from the geometry, we can write r is equal to x cot theta. And if we substitute this in the first equation and differentiate this with respect to x and equate it to 0, then we can get W is equal to pi r squared p minus 2 pi r EAB cot theta. This is a simple thing which can be done very easily. So this gives us the work required to produce a heat Eg. In the absence of surface energy, that means if we let EAB 0, then we have got W is equal to pi r squared P. Now P here is the hardness or the plastic yielding stress. So obviously, when it is digging into a softer material, there will be plastic yielding. And here we can write W is equal to pi r squared. Earlier we have written PM, but here we are writing P for generality. So W is equal to pi r squared P when there is no surface energy. But if surface energy is there, then you will need less force for indentation. And that is clear if you look at the previous equation. W is equal to pi r squared P minus 2 pi r EAB cot theta. Okay? So in the presence of surface energy, we need less load for the indentation. Now we apply a tangential force F. And tangential force F, as we have discussed earlier, is the projected area. Projected area again is pi r square and multiplied by tau. Tau is the shear yield stress of the material. So this gives the abrasive coefficient friction to be F by W is equal to tau pi r square, frictional force F, and W, normal load, as shown earlier, pi r squared P minus 2 pi r EAB cot theta. So we can simplify this by writing tau by P 1 by 1 minus 2 by RP EAB cot theta. Now here again, we can look at it in a very clear way that if you let the surface energy to 0, then mu AB becomes tan theta by pi. This is what we have seen earlier in the abrasive coefficient of friction. We can see this. There, mu plowing is tan theta by pi. Okay, so this is quite clear that when surface forces are operative, less force is needed for indentation. And again, the coefficient of friction takes a form as shown here. And again here, letting the surface energy 0, we get back to the original equation. Now we look at the adhesion in a little more detail. And tribology, adhesion is a very important issue. Friction and many other phenomena where uneven lubrication are affected or influenced by surface energy to a great extent. Adhesion in macroscopic and microscopic or nanoscopic levels have their different origins. Macroscopic adhesion we have discussed, which could be just a solid state welding at the peak of the asperity, or it could be mechanical action between the asperities. Whereas in the microscopic or nanoscopic or atomic level, intermolecular forces are more important. Here normally we consider van der Waals forces, and as we have shown and discussed before, when the two surfaces are brought together, the contact is only at the peaks of the asperity. But the picture shown here will not be useful for our microscopic or nanoscopic consideration, because there we need a very smooth surface, because otherwise the intermolecular forces will not be operative. Now, due to the attraction and repulsion between the individual atoms and molecules, to ideally smooth and clean surfaces will repel each other before the equilibrium separation. Here we have shown it at Z0 and will attract when it is above this separation. A typical separation curve is shown here, and we can write the force per unit area in a very typical form as P is equal to minus A Z to the power minus N plus B Z to the power minus M, where M is greater than N. And here A, B, M, and N are constant, depending on the physical nature of the solids. That is, whether they are ionic, metallic, or van der Waals. Now, work done to separate the two bodies would, of course, be PdZ, that is the area enclosed by the curve and the horizontal axis. So it will be P dz, Z0 to infinity. And this, if we do the integration, will give you M minus N times A divided by M minus 1 multiplied by N minus 1 and the whole multiplied by Z0 to the power N minus 1. So this is the work of adhesion, or in many cases, we can call it separating or pull-up force. And as we have seen before, for dissimilar metal, the delta gamma or the work of adhesion, sometimes it is called Dupre energy, gamma 1 plus gamma 2 minus gamma 1, 2, where gamma 1 and gamma 2 are the surface energy of the two surfaces, and gamma 1, 2 is the surface energy of the interface. Okay, so this we have seen before, but this is for completeness. Now, there are many different models of adhesion. This is a very big topic, and obviously we cannot go to the in-depth detail of this topic. But very briefly, we mention the two main models. There have been many more models developed since these two came up. These are called JKR, Johnson, Kendall, and Roberts, in 1971. And then little later, DMT, Nirajuin, Muller, and Tomborov, 1975. These are the two main models. And they very well can predict the pull-up force or the force of adhesion. Johnson, Kendall, and Roberts proved this and did a lot of experimental results have been shown up to prove their theoretical backing. So we go into a little bit more into the detail. Going to more into the detail of adhesion model of JKR, Johnson, Kendall, and Roberts model. Attractive forces, that is short range forces, are assumed here. Are the Johnson, Kendall, and Roberts assume that the surface molecular forces act within the contact. If you look at this diagram here, 2A is the deformed contact area, and 2A dash is the contact area after taking care of the intermolecular forces. That means the intermolecular forces increase the contact area. And taking this into account, they have shown that the pull of force is 3/2 pi gamma A. Again, gamma is delta gamma, but we have written gamma here for simplicity, is the Dupre surface energy, and A is the contact radius. But Derivative or DMT model considers a completely different contact phenomena. They consider that the surface molecular forces act outside the contact zone. And they have their reasons, obviously, but we cannot go into the detail of the calculations. But the total pull of force, according to their equation, is 2 pi gamma A. This is not very much different from the JKR model, which is only 3/2. So you see the two models don't give much different results, but the assumptions are quite different. And around mid-70s, there were a lot of discussion about these two assumptions. And Muller and Tabor in Cambridge, they came up with a solution. They said that these two solutions are not contradicting. They are basically the two limiting ends of the same solution. And they came up with a parameter phi naught, which is given by R gamma square by E square Z naught cube. R is, of course, the contact radius, gamma is the surface energy, E is the elastic combined elastic modulus, and Z naught is the equilibrium separation. If this is less than 0.3, then DMT model will apply. But if this is greater than 3, JKR model is applicable. So this means that these two models are not different in any way. They apply for two different ranges of materials. So the DMT model is favored for small values of R. That means the contact radius is small and gamma is small. Obviously, you can see that in the first equation, phi naught is equal to R gamma square by E square Z naught cube. And obviously, E has to be large in this case for DMT model to be applicable. And similarly, for JKR model to be applicable, R and gamma should be slightly small, slightly larger, and E should be slightly smaller. So there is no contradiction except that they apply for two different kinds of material. As I say, this is a very big topic, and obviously in this short course we cannot go into the detail. But around this time there was a lot of discussion, and Tabor came up with this. Of course, following Muller, came up with this solution. Now, coming back to our original idea that the surface forces will be acting when the two surfaces are smooth and clean. Clean because if the two surfaces are not clean enough, there will be surface layer, oxide or some other layers. And these layers will not allow the two surfaces to come within few angstroms for the intermolecular forces to be operative. And the same applies for surface contamination and surface roughness. If surface roughness is large, then of course the same problem will occur. The two surfaces will not come into contact very closely, and surface molecular forces will not apply. Again, with this discusses the contaminant layer, and there are different kinds of contaminant layer, and we'll not go into the real details of this, but we'll discuss this roughness effect a little bit more in detail. Around 1975, Tabor and Fuller again did some work, both experimental and theoretical, and they came up with a factor theta, which is E star sigma 3/2 or half to the divided by R gamma. Now here, obviously the E star or E dash is the combined elastic modulus. Sigma is the standard deviation of the surface asperity heights, and R is the asperity radius. And gamma is the surface energy. So they said that this gives a measure or the ratio of elastic forces necessary to deform an asperity of radius r to a depth of sigma, and the denominator is a measure of the corresponding surface forces. So theta value is in the region of 10. If theta value is in the region of 10, then adhesion is very small. Obviously, that is very clear, because if theta is large, then gamma in the equation can be seen in the denominator being has to be small. Similarly, Johnson came up with another factor called plastic adhesion index, given by lambda is equal to pi square r h4 sigma by 18k square gamma square. Here h is the hardness, sigma is again the standard deviation of the surface asperity heights, and k is the combined elastic modulus. And again, this gives a ratio of the plastic forces necessary to deform an asperity to a depth of sigma, and the denominator gives the corresponding surface forces. Again, here they have found out that if the lambda values in the region of 0.125, adhesion is insignificant. So I think these two parameters are very useful for practical engineers to see when to use clean surfaces and when not to use rough surfaces. So with this, we end here. But again, I repeat here that this is a very involved topic, and it takes a very long time to complete this. We have given a very bird's eye view of the whole course. Okay, so we completed here, and we meet the next slide.